All right, so I want to show how to derive the sine equation from first principles. And while we're at it, I will also show you where any trig substitutions or identities come from as we go. So remember that if we're trying to find the derivative from first principles, we're going to be using this idea that we're essentially doing rise over run, where we're looking at two different y values over the distance between those x values. And then we're taking the limit as h approaches 0. In other words, we're looking at what happens as we squeeze those points closer and closer together. So if we're looking at the sine function, then we're going to be looking at this. Sine of x plus h minus sine of x all over h. So then one big question is, what the heck do we do with sine of x plus h? So I'm going to draw a little diagram and see if we can figure out something about sine of x plus h. So we have a diagram like this where we have x degrees and h degrees like that. I'm going to label the different points. Let's just call this O for origin. And then we're going to create a right triangle like this. So this will be point A. And then I'm going to do one thing here that helps out with this proof, which is to create a right angle right here. So I have another right triangle that I can work with. And then I'm going to go down from there. So let's call this point B. We're going to call this C here. And then I'm going to go directly parallel to AB to make a new point right here called D. And the last point I'm going to name is E. Now, something that's a little tricky to figure out is, but will be important later, is what is this top angle right here? And the way you can do it is by just remembering that we have a bunch of right triangles and then you have vertical angles also. Visually, you can imagine what I'm going to do is reflect the triangle over AE, so flip it horizontally, and then I'm going to rotate it up 90 degrees and it's going to match up in there. So let's look at how the angle transfers. So this angle right here is 90 minus x. This angle on the other side of the vertex is also 90 minus x, which then means that this angle here has to be x itself. Well, then I told you that I made a right angle at the point C. So that means on the other side is 90 minus x, and then that means up here at the top is x again. Okay, so that'll become important in a little bit, that we know that the top angle also has to be x. So let's write down what we know about sine of x plus h. First thing I know is that sine is just opposite over hypotenuse. So sine of x plus h is the opposite, AE, over the hypotenuse, OE. I can split that up to be two different pieces. AE is really AD plus DE, and I can split that up into two different fractions, both over OE. See how I did that? The top AE can be split up into the bottom part from A to D plus from D to E. So AD over OE, DE over OE. Then AD is part of a rectangle and BC is on the other side. So that right there, those are equal to each other because they're rectangles. So this equals BC over OE and still DE over OE. So now there's a couple problems here. These are not pieces of a right triangle that I can recognize. BC and OE aren't even on the same triangle, and DE and OE aren't on the same triangle. So the nice trick that you can always use is multiplying by the number 1. So if I look at OE, I can think of OE as being a hypotenuse with angle H in it. And so angle H is opposite of EC. So I'm going to go times EC over EC. I'm always allowed to multiply by anything over itself because that's equal to 1. And then over here, similarly, on this other piece, I have DE and OE. And I'm going to multiply that by EC over EC. I think something is a little bit wrong. Yes, on my first triangle, I don't want to use EC over EC because EC doesn't have anything to do with BC, excuse me. So I'm going to multiply by OC over OC. I knew when I made this video I'd make at least one mistake. So OC over OC. Okay. So now the last thing we're going to do, or second to last thing we're going to do, is flip-flop the denominators. So now we have OC over OE times BC over OC. Flip-flopping these denominators, DE over EC, EC over OE. All right, so now I'm going to write on top of that with what these different ratios are. So if I look at OC over OE, that's going from here to there, OC over OE. And then we can see that those are the adjacent and the hypotenuse for angle H. So this is cosine of H. Then if I look at BC over OC, that's for angle X, opposite and hypotenuse. So that's sine of angle X. And then DE over EC, DE over EC, let's use a different color here. So here's DE over EC. Remember that we found this is angle X here, so that's cosine of angle X. And then EC over OE is opposite and hypotenuse for angle H. So now we have our formula. So we can use that to continue. Remember, our original goal was to find the derivative. So we're going to continue with that. Limit as H approaches 0. So now we know we can write it as cosine H sine X plus cosine X sine H minus sine X all over H. I'm going to split this up into two different pieces and distribute the limit to each of them. So the two different pieces look like this. Limit as H approaches 0 of cosine H sine X minus sine X all over H, plus the other piece, cosine X sine H over H. This one on the left has a sine of X in common, so I can factor that common piece out in front of the limit. You might be wondering, wait, how can you factor out something involving X in front of the limit? And the answer is because the limit refers to as H approaches 0, not as anything to do with X. So I can take sine of X out in front because it doesn't have the same variable as the limit. So I hope you can see how the sine of X distributes back inside. And then same idea with the second piece. Cosine X times the limit as H approaches 0 of sine of H over H. Okay, so now there's two things I need to do. I need to figure out what happens with H approaching 0 for this limit and what happens for this limit right here. Okay, so what I'm going to do is I'm going to look at a very small angle on the unit circle. So we're going to draw a little unit circle in here, right? So you draw your axes, you draw a cute little circle. But we're only really looking at what happens when you have a small angle, like even smaller than what I'm drawing. I just can't draw super accurately. So if I look at this right here, I can fit a little triangle there. And what's nice about measuring in radians is that the length of the arc right here, the length of the arc is equal to theta. The length, the height of the triangle is equal to sine of theta. And what you can see is that as we get closer and closer to zero, that leg of the triangle gets closer and closer to the outside of the circle. In fact, they are so close as to practically be equal. You might see this sometimes referred to as small angle approximation. So for a small angle, theta is equal to sine of theta because the arc length is just about the same as the height of the triangle. And I'm allowed to do that because I'm looking at the limit as h approaches 0. Similarly, if I look at cosine here, cosine, this leg right here gets really close to 1. So you can say cosine of theta, ooh, yellow is a terrible choice. Cosine of theta, I'm going to switch to orange. So there you go, orange. Cosine of theta is approximately 1. So let's use those small angle approximations to finish out our proof. We have sine of x times the limit as h approaches 0 of 1 minus 1 over h plus cosine x times the limit as h approaches 0 of h over h. And that means that we have here a big ol' 0 over h, here a big ol' 1. So sine times 0 plus cosine times 1 is cosine of x. So now we've proved from first principles and a little bit of trigonometry and a weird little small angle approximation that the derivative of sine has to be cosine. So thanks for watching. Please comment, ask questions if there's anything else I can do to help.